In today's video, we will look at a technique of differentiation known as implicit differentiation. This video will be largely divided into two parts. The first part will be looking at just examples of how we can do implicit differentiation. Then, once we have a foundation for implicit differentiation, we will use that technique to go ahead and derive the derivative of inverse trigonometric functions. So to begin with, let's consider the equation x squared plus y squared equals 25. And let's say that we want to know the slope of a tangent line at a specific point. Well, remember, slope of a tangent line is dy dx. So we need to find dy dx. But this is not an explicitly defined function. This is y being implicitly defined as x. What we do then is just take d dx of every single term. Like so. Now it's just a matter of doing the differentiation that we've been studying so far. The derivative of x squared is 2x. The derivative of y squared, right, that's a power rule, so that's going to be 2y. But since y is a function of x, we have to use chain rule, right, dy dx. Right, then the derivative of 25 is just 0. So we have 2x plus 2y dy dx is equal to 0. Now we just have to solve for dy dx. Y equals negative 2x. And we find that dy dx is equal to negative x over y. Now, let's look at x cubed times sine of y plus y is equal to 4x plus 3. Right? Well, we want to do the same thing. So differentiate term by term. X cubed times sine of y. Well, this is a product of two functions. So we have to use product rule. Right? Product rule says, take the first function, multiply by the derivative of the second function. Right? Of course, we have to do chain rule as well and say dy dx plus the second function times the derivative of the first function. Now we take d dx of y, which is just dy dx. That's going to equal just 4. d dx of 4x is 4, and d dx of 3 is 0. All right, now the idea here is we want to keep dy dx terms all on one side. So what we'll do is take the terms that do not have a dy dx, which are 3x squared sine of y and 4, and move them to one side. Let's just move this 3x squared sine y over to the right-hand side by subtracting it. Now what we can do is we can factor out a dy dx from these terms on the left-hand side. So let's go ahead and do that. Now we just have to divide by this x cubed cosine of y plus 1. And we'll have dy dx is equal to 4 minus 3x squared sine of y all over x cubed cosine of y plus 1. All right, now let us consider once again the circle of radius 5, which was x squared plus y squared equals 25. Except this time we want to find the second derivative. Now remember, to find a second derivative, we're taking the derivative of dy dx. Well, we've already found what dy dx was equal to negative x over y. So if we wish to find the second derivative, so d squared y over dx squared, what we want to do is find d dx of negative x over y. And again, we're going to have to use implicit differentiation here. Right, now this is a quotient rule. Right, so it'll be negative, right? So I'm going to use constant multiple. Now quotient, denominator, times the derivative of the numerator is 1, minus the numerator times the derivative of the denominator, which is dy dx, all over the denominator squared. But dy dx is up here. It's negative x over y. So let's go ahead and plug that in. Well, now what we can do is do algebraic simplifications, right? So distribute this negative through first. Now in the numerator, we need to find a common denominator, which in this case is y. Dividing fractions, multiply by the reciprocal. And at this point, I have to apologize because right here I forgot to put in an x, right? So this then should be x squared, that should be x squared, this should be x squared. Now we're not quite done yet. Notice this y squared plus x squared. Up here it's given to be 25. Right, so we can just write 25 over y cubed, and that would be a second derivative. And again, I forgot the negative, so let's do that. That's a negative, that's a negative. This should be a negative here. So negative 25 over y cubed. All right, we're going to have one final example for implicit differentiation. All right, we're going to be looking at a curve that's known as the folium of Descartes. So that curve is given by the implicit equation y cubed plus x cubed minus 3xy is equal to 0. We wish to find the tangent line at the point 3 halves, 3 halves. All right? We have to follow the same steps. All right, so 3y squared dy dx plus 3x squared minus, now this is a product rule. So let's actually write the 3 on the outside, minus 3 times first times derivative of the second plus second times derivative of the first, and that will equal 0. All right. Let's distribute that negative 3 through. Now what we want to do is move all of the terms that do not have a dy dx over. All right, so we're going to move this 3x squared and this 3y over to the other side. We can now factor out that dy dx from the left-hand side. And finally, we can divide by that 3y squared minus 3x. Notice that both the numerator and denominator have a common term, has a common factor of 3, so we can also cancel out the 3's and have y minus x squared over y squared minus x. Now remember, dy dx is slope of tangent line. Since we want this at the point 3 halves, to find the slope, we take dy dx and evaluate it at the point 3 halves. Doing this, we'll have 3 halves minus 3 halves squared all over 3 halves squared minus 3 halves. Let's factor out a negative. All right, then we can write the numerator as 9/4 minus 3 halves. We'll have the denominator as 9/4 minus 3 halves. And if we look at this, we don't have to do any arithmetic. That winds up being just -1. So the tangent line is y equals -1 times x minus 3 halves plus 3 halves. And so we'll get -x plus 3 as our tangent line. What we can now do is go ahead and look at the derivative of the 6 inverse trigonometric functions. What we will wind up doing in this video is only derive 3. The other 3 will just be given, and their derivation will be left to you, the viewer, to do. The 3 that we are going to look at in this video are the 3 that we will be using again later in the series when we look at integration. They are the inverse sine function, the inverse tangent function, and the inverse secant function. Let's begin with y equals inverse sine of x. Now remember, by definition, this is the same as x equals the sine of y. So what we will do is differentiate this implicitly, right? Then we'll be able to solve for dy dx, but y, is inverse sine. So what we're going to do is we're going to go, okay, well, d dx of x is equal to d dx sine y. This leads 1 equals cosine of y times dy dx. And so what we find then is that dy dx is equal to 1 over the cosine of y, but y is the inverse sine, so this is cosine of the inverse sine of x. We have to try and simplify that. Well, we're going to use right triangle trigonometry. There's our angle, or right angle rather. Let's say this represents the angle y, which is inverse sine of x. Well, sine of that angle, remember by right triangle trigonometry, sine is opposite over hypotenuse. Right? So the opposite side would have to be x. The hypotenuse has to be 1. That is from right up here, x equals sine of y. Then what is this missing length? Well, we use Pythagorean theorem. A squared plus b squared is equal to c squared. So this would have to be the square root of the hypotenuse squared minus opposite squared. That is, this is the square root of 1 minus x squared. Also notice that y itself, right, the range of the inverse sine function, is negative pi over 2 to pi over 2. So y is an angle between negative pi over 2 and pi over 2. That means the inverse sine is negative pi over 2 to pi over 2. Cosine is totally positive over that range. Right? It's the right half of the unit circle. With all of that, we can conclude that the derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. Let's now look at the inverse tangent function. Y is equal to inverse tangent of x. Now again, by definition, this means that x is equal to the tangent of y. So just like we did with the inverse sine, we will differentiate this latter equation using implicit differentiation. That is, d dx of x is equal to d dx of tangent y. This means that 1 is equal to secant squared of y dy dx. And so dy dx is 1 over the secant squared of y, which is 1 over secant squared of inverse tangent of x. And again, what we have to do is try and simplify that. So we want to evaluate secant squared of inverse tangent. We will once again turn to right triangle trigonometry. So there's our right triangle. We'll say this is the angle y. Now, tangent is opposite over adjacent, right? So opposite is x, adjacent is 1. We can then find the hypotenuse using Pythagorean theorem, and that is the square root of x squared plus 1. Secant is 1 over the cosine, right? So really what we can do is we can write this. It's kind of like cosine squared of the inverse tangent, right? And of course, cosine is adjacent over hypotenuse. We also have to take into account that the range of the inverse tangent is negative pi over 2, 2 pi over 2, not including those two endpoints, right? Right, so much like we did up here, we have to look here and we have to go, okay, since we are dealing with a cosine, once again, it is totally positive over this range, right, between negative pi over 2 and pi over 2. So we're going to have that cosine squared of the inverse tangent of x is 1 over the square root of x squared plus 1, all squared, which is 1 over x squared plus 1. We can therefore conclude that the derivative of the inverse tangent of x is 1 over x squared plus 1. Finally, we will now look at the inverse secant function. Just as with the previous two, we will write that to mean x is equal to the secant of y, and then use implicit differentiation on this latter equation. That is d dx of x will equal d dx of secant of y. So 1 will equal secant of y times tangent of y times dy dx. And so dy dx we find is 1 over secant y times tangent y. Right, but y is inverse secant, so that's secant of the inverse secant of x times the tangent of the inverse secant of x. Now, of course, the secant of the inverse secant, they drop out, they cancel each other out rather. So we get x times the tangent of the inverse secant of x. We just have to determine what the tangent of the inverse secant is. And we will again turn our attention to a right triangle. Right? So secant of y, right? So secant is 1 over cosine. Since cosine was adjacent over hypotenuse, secant is hypotenuse over adjacent. So this will be x here. This will be 1. Missing side will then be the square root of x squared minus 1. Also, the range of the inverse secant is 0 to pi, excluding pi over 2. Now, for 0 to pi over 2, tangent is positive. So that'll just be square root of x squared minus 1 over 1. However, if we look at pi over 2 to pi, now tangent is negative. So it'll be negative square root of x squared minus 1. What we then find is that dy dx winds up being 1 over x times plus or minus square root of x squared minus 1. This will be 1 over, we can factor out that plus or minus, right, as plus or minus x. Right, plus or minus x. Now, x can be positive or negative, right? Again, x will be positive from 0 to pi over 2. X will be negative from pi over 2 to pi. Notice in either case, plus or minus x will wind up being positive. So we can use that to write this. 1 over the absolute value of x times the square root of x squared minus 1. And we can thus conclude that d dx of the inverse secant of x is 1 over the absolute value of x times the square root of x squared minus 1. We will now provide a list of all 6 derivatives. All right, so we already saw the inverse sine, which was 1 over the square root of 1 minus x squared. The inverse tangent, which is 1 over x squared plus 1. and the inverse secant, which is 1 over the absolute value of x times the square root of x squared minus 1. The remaining three are left to you, the viewer. However, they are the derivative of the inverse cosine is negative 1 over the square root of 1 minus x squared. The derivative of the inverse tangent, I'm sorry, not inverse tangent, of the inverse cotangent is negative 1 over x squared plus 1. And then the derivative of the inverse cosecant would be negative 1 over the absolute value of x times the square root of x squared minus 1. Notice that interesting property. The inverse co-functions are just the negative derivative of their corresponding function, right? So the derivative of the inverse cosine, the derivative of the inverse cosine function is negative derivative of the inverse sine function. That is an interesting relationship that will come into play when we start to study integration. We will now consider several examples of taking the derivative of inverse trigonometric functions, beginning with the derivative of the inverse sine of 2x cubed. And so from our previous work, we'll have 1 over the square root of 1 minus what we're taking the inverse sine of squared. Then chain rule dictates we have to multiply by the derivative of 2x cubed. Simplifying all this, we get 6x squared over the square root of 1 minus 4x to the 6th. Let me just rewrite this. And there it is. Let's now consider the derivative of the inverse tangent of x squared. Again, by the work we've done, it's 1 over what we're taking the inverse tangent of squared plus 1, and now chain rule says take the derivative of x squared. And so we get 2x over x to the 4th plus 1. Now let's find the derivative of the inverse cosecant of e to the x plus 1. This will be negative 1 over the absolute value of what we're taking the inverse cosecant of times the square root of that squared minus 1. And now chain rule says take the derivative of e to the x plus 1. Let's go ahead and simplify this. Now, e to the x will always be positive. Add a positive to a positive is still positive. So we can actually get rid of those absolute values. Expanding out the e to the x plus 1 squared e to the 2x plus 2e to the x. Then it'll be plus 1 minus 1, which is 0. And of course, all times e to the x, so let's put e to the x in the numerator. We can now factor out. Sorry, no, we can't. It looks like that's going to be it. Let's just leave it like that. We could factor out a square root e to the x, but it's not really worth it. Now there is one more technique that we want to look at, and we're going to do that via example. The final application of implicit differentiation that we will study in this video can be used to find the derivative of a complicated function much like this one. Now we could use quotient rule on this. However, the algebra is going to be really hideous, right? So let's make use of implicit differentiation, and knowing that if this was a natural logarithm of this, we could simplify it so much. Well, let's go ahead and take the natural log of both sides. And using laws of logarithms, we can rewrite this as 2 times the natural log of x plus 1 plus the natural log of 2x squared minus 3 minus 1/2 the natural log of x squared plus 1. Let's use implicit differentiation on this, right? So we'll have f prime of x over f of x is equal to 2 over x plus 1 plus 4x over 2x squared minus 3 minus 2x over 2 times x squared plus 1. But of course, those 2's will cancel out, and so we can actually just write that as x over x squared plus 1. This would mean that f prime of x is equal to f of x times that entire thing. Just replace f of x with what we originally said the function was, which is x plus 1 squared times 2x squared minus 3 all over the square root of x squared plus 1 and let's just leave it in that form. Right, simplifying that really serves no purpose. And now there's our derivative with far less algebra than if we would have tried to differentiate this directly. This technique is called logarithmic differentiation. right? And the procedure is as follows. Take the natural log of both sides, use implicit differentiation, then solve for f prime. So that concludes this video on implicit differentiation. That also happens to conclude the unit on the derivative. In the next video, we will begin looking at applications of the derivative by starting with related rates.